run. Later, this idea will help us develop the notion of envelope curve. Okay, you have some idea about the envelope curve when you do the long run and the short run cost analysis. Okay, so I think all of you have some idea about the envelope curve. Do you?
Yes, ma'am.
Yes, ma'am.
So mathematically, what is the implication of enveloping, etc., that we will be able to understand. However, that application of envelope idea that will come only in context of constraint optimization. In case of unconstant optimization, we will only study the slopes of the short run and the long run factor demand curves. Okay, so let's start with that. Long run and short run, long run vis-a-vis short run. And here we will apply Le Chatelier's principle, that it's not that you should have a very good idea about the Le Chatelier's principle. So let's look at the matter. You will understand by the knowledge you gained so far, by that only we will be able to find out, or we will be able to show what will be the shape of the slope of the short run factor demand function and what will be the slope of the long run factor demand function. So as you know, in general, short run is a period when some factors of production remain fixed. So the model we have considered, there we have two factors, x1 and x2. So, in context of short run, what we can do, I can consider x1 as the variable factor, whereas x2 as a fixed factor. So we will keep x2 at a particular level, say x2 naught, and will vary the volume of x1 in the production process. And long run is a situation when all factors of production will be variable. So in our model, both x1 and x2 will be variable in context of long run. So short run means x1 can vary, however x2 is fixed at a particular level, x2 naught, and long run indicates a context when both the factors of production are variable. Actually, therefore, the past analysis we did, just the last thing we did, the way we developed the input demand function, etc. So everything is based on long run because we didn't fix a factor. We considered all factors are variable. Okay, so the analysis we actually covered so far, that is the long run analysis. Typically, now we are considering the short run phenomenon. So we are considering the same profit function, which is revenue minus cost. However, in the output function, P into Q, in the output function, I am keeping x2 fixed at a particular level, x2 naught, minus w1 x1 minus w2 x2 naught. So if you look at this expression, I hope you are understanding this second part, w2 x2 naught, this will behave just like a fixed cost. Okay, so if you consider the total cost equation, there can be a fixed cost and there can be the variable cost. Now, if one factor of production in a two-factor model is fixed, this W2 x2 naught, that is fixed amount. So this is as if the fixed cost component of the cost equation. So cost equation is basically W2 x2 naught plus W1 x1. W1 x1 is the variable cost, W2 x2 naught is the fixed cost. If you consider this particular profit function, here there is a single decision variable, and that variable is nothing but x1. Once we define the profit function, in the next step, if we like to maximize it or optimize it, first we have to consider the first order condition. So we will consider del pi by del x1, del pi by del x1. The similar kind of thing we also did earlier. Here the speciality is x2 is not varying. Now del pi by del x1, that can be presented by pi 1, and just like previous example, I'm considering a competitive context. So price is given from outside. Price is not a function of quantity. It is a parameter. Okay. So when we are taking the derivative, del pi by del x1. It is p del f by del x1, which we are indicating by x1. And from this expression, we are getting minus w1. First order condition tells us this expression will be equal to 0. So this is the first order condition. Now, if you want to find out the second order condition, actually the situation is just like a single variable case, which you did in your earlier semester. So here we will be not able to frame the Hessian determinant. Rather, we will get a single component, del square pi by del q1 square, del x1 square. Okay. So we are considering pi 1, 1, which is the second derivative of pi. Now, if I consider the second derivative, there is this p, and this f1 will be differentiated with respect to x1 once again, which notationally is presented by f11. Okay, so pi 1, 1 is nothing but p f11. And the requirement of maximization or the sufficient condition to have a maximum profit will be given by this negative sign. Okay, so if you now you have idea about the Hessian determinant. So if you think about the Hessian determinant, actually we are getting the only first component in the Hessian determinant. Okay, pi 1, 1, only the first component in the entire Hessian determinant, and that is given by pf11. Sufficient condition for maximization is given by the fact that this should be less than 0. Any question regarding how we are incorporating the idea of short run, how we are maximizing profit, how we are deriving the first and second order conditions? Any question? So once we get the value of x1, we can present at optimum, the value is given by x1, which is a function of w1, p, and x2 naught. Okay, so w1, p, and x2 naught. Given the amount of capital, we are trying to find out the optimum utilization of labor, optimum usage of labor, or optimum demand for labor. So this is the concept. Now for the long run, I used the notation star, etc. Or for the previous analysis, I used the notation star. So here to differentiate the short run and the long run, I am bringing the notation S. So X1S is the short run factor demand. And this is a function of W1, P, and X2 naught. The long run factor demand was function of W1, W2, and P, whereas the short run factor demand is a function of W1, P part is common. However, instead of W2, here we are bringing the amount of the second input, which has been kept fixed at this particular level. X1S stands for the short run demand. Okay, so this part is already covered, that W2, X2 naught is a fixed cost component, etc. So if this is the situation, the slope of the factor demand curve will be given by del x1s by del w1, del x1 short run by del w1. Once we get this expression, we can put this in the profit function to get the value function. So in the next step, we are doing the same thing. To derive this del x1s by del w1, or to derive the factor demand curve, or to have understanding about the slope of the factor demand curve, we are considering the optimum value function. Okay, so this is the profit equation, which is optimum in nature, because I have replaced any x1 by a specific value x1s. So the optimum value function is given by P into, I think I have considered the first order derivative. What you can do, before writing this expression or before coming to this expression, you can write the profit function as well. And then you can consider the first order derivative. Okay. So if you write the profit function, it will be P. Today, I do not have the DG board. Okay. So therefore, I will not able to write. Okay. However, if you need everything, in that case, I have to type in the Word document. So if you understand, it's fine. And however, if you have any difficulty, please tell me. I'll, write it in the Word document. This is the only option today I have. Actually, I am in different location. So, so if you have pen and paper, I hope all of you have pen and paper. So would you please write down the optimum profit equation first? The profit equation, would you please write down? That will be P f of x1s, comma, x2 naught minus w1 x1s minus w2 x2 naught. Now, if that is the profit function, if we take derivative with respect to x1s, are we getting this first order condition?
Yes, ma'am.
Yes, ma'am.
Okay. So differentiating this, okay, so this expression is with you. This expression is with you. This first order condition is with you. Now we will take derivative of this expression with respect to W1. We will take derivative of this expression with respect to W1. So for F1, you have to apply the chain rule. F1 is a function of x1s and that x1s is a function of W1. So please apply chain rule. So P into basically del square f by del x1s square, that kind of thing we are considering. So, that will be presented using this chain rule because we are taking the derivative with respect to W1. So del f1 by del x1s into del x1s by del W1. So please write down P into del f1 by del x1s into del x1s by del W1. And from this second expression, you will get minus 1. From this second expression, you will get minus 1. That is equal to 0. And then if you readjust, you will get this equation P f11 del x1s by del W1, that is equal to 1. In the left hand side, there was minus 1. So we can bring 1 here. So if we take derivative of the derived first order condition with respect to W1, we are getting the expression for del x1s by del W1. So in the next step, I'm keeping del x1s by del W1 in the left hand side and remaining factors in the right hand side. Now, by the sufficient condition of the second order, we are getting second order sufficient condition tells us this F11 will be negative. P is price and that is positive. So this entire factor in the right hand side is negative, which in turn indicates the short run factor demand curve is negatively sloped. The short run factor demand curve is negatively sloped. So this result we got also in case of the profit maximizing exercise and then considering the value function approach, etc. when we considered both the factors are variable. We got both del x1 star by del w1 and del x2 star by del w2. These are negative. So similar kind of result we are getting in the short run context too. Here the number of factors is 1, and here we are getting del x1s by del w1 is negative, downward sloping. Okay, downward sloping. Any question? Next, we will compare the short run factor demand with the long run factor demand. The short run factor demand with the long run factor demand. To compare the slope, compare this slope with the slope of the long run factor demand where x2 varies. We consider the difference between the slopes of the long run and short run factor demand functions. So we will consider slopes of the long run and the short run factor demand functions. Okay. We assume del x1 star by del w1 is exactly equal to del x1 L by del w1. It is only a notational matter. Previously, we used the star notation. Therefore, I am marking the fact that please treat del x1 star by del w1, which you derived earlier, is equivalent to del x1 L by del w1, where x1 L is the long run factor demand for x1. This is the demand for factor 1, when x2 can vary. When x2 can vary, this is the demand for x1 when x2 is variable. Okay. So last day, actually, we got this expression. When we consider del x1 star by del w1, we typically got this expression. Can you remember, or shall I move back to the slide where we derived del x1 star by del w1? Is it fine?
Can you please show this?
Okay. Okay, so this was the expression. We did several steps and we got it. Del x1 star by del w1. Can you remember we did all these things in the last class?
Yes, ma'am.
Okay, and we got this expression. So would you please write down, instead of star, please write down L. Del x1 L by del w1. Del x1 L by del w1. That is F22. 2 is coming from the x2 component. F22 divided by P into F11 F22 minus F12 square. Okay, so all of you could write it down. Del x1 star or del x1 L by del w1. Is it fine?
Yes, ma'am. Yes, ma'am.
Okay, so this expression already you have with you. Okay, F22 by P into F11 F22 minus F12 square. Now during the exam or any time when you will be able to when you need to compare the short run and the long run, you have to do the past derivation as well. Since we did it in the earlier class, therefore here we are not doing all the steps when x2 is variable component. However, when you will present something, you have to do that part as well. So I am taking the expression which we derived in the last class minus del x1 s by del w1, just we derived, that is 1 by p f11. 1 by p f11. Okay, 1 by p f11. So please take LCM. Please take LCM and derive the value, derive the difference. If you adjust the thing, please check whether you are getting the value presented in the slide or not. Okay, so don't copy this value. Rather, Please take LCM and check whether you are getting this value or not. Please do it. Denominator will be, P F11, into F11, F22 minus F12 square. This will be the LCM. So please derive the value and tell me whether you are getting this result or not.
Ma'am, this value is only coming. Yes, ma'am.
Yes, ma'am.
Very good. So rest of the students, could you complete?
Yes, ma'am.
Yes, ma'am.
So this is the value. Now once we get this value, we will like to check what will be the sign of this difference. What will be the sign of this difference, whether it is negative, positive, etc. Now numerator is a whole square. Numerator is a whole square. So it is always positive. In the denominator, from our previous discussion, we got that F11 less than 0, because it is the maximization problem, and maximum takes place if the principal minus of Hessian determinant alter in sign starting with negative. Okay.
Ma'am, sorry ma'am, but I couldn't understand why there will be F12 square in the denominator.
Oh, we are getting F12 square in the numerator. What is your...
Why will there be F12 square? Because I am taking the LCM, so I am multiplying it with F11. So it should be F22 into F11 minus F11.
Are you talking about the LCM or
Yeah, the value that came. Yes, ma'am.
Okay, so denominator is fine to you? This is fine?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay, so you have to multiply this thing, this thing with...
Okay. Yes, ma'am. Yes, ma'am. Yes, ma'am. Okay. Got it.
F11, F22.
Yes, ma'am.
What is?
Yes, ma'am. Yes, ma'am.
Okay. So once we get this, second order conditions or the principal minors of the Hessian determinant, signs of the principal minors of the Hessian determinants for a profit maximization exercise ensure that this will be negative, this will be positive. So the entire thing ultimately will be negative. The difference will be ultimately negative. Now please look at the expression. It is del x1L by del W1 minus del x1S by del W1, where both del x1L by del W1 and del x1S by del W1 themselves are negative. Themselves are negative. Sign of the first component is negative. Sign of the second component is negative. So both the factors are negative. So if we consider the negative issue here, what we are getting, minus of something, minus of something. So it is plus something. So minus of something plus something. So to maintain the negativity of these difference, what we need that the absolute value of del x1L by del W1 should be greater than that of del x1S by del W1. I'm repeating. Both the components in the left-hand side themselves are negative. Themselves are negative. So as both the components are negative, if we want to have this difference to be negative, what we need that mod x1L by del W1 will be greater than mod del x1S by del W1. Am I right?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So that it indicates, the long run supply curve will be steeper than that of the short run, long run demand curve, factor demand curve will be steeper than that of the short run factor demand curve. Long run factor demand curve will be steeper than that of short run factor demand curve. However, we will follow the Marshallian convention when we will draw the diagram, present the long run and the short run factor demand curves. Along the vertical axis, we will measure W or W1 or the price of factor 1. And along the horizontal axis, we will measure the quantity demanded for factor 1. So graphically, if we like to present the curve, the long run supply curve should be flatter than that of the short run factor demand curve. The long run factor demand curve will be flatter than that of the short run factor demand curve because we will plot inverse factor demand curves. To maintain this, we need that the absolute value of the first factor should be greater than that of the second factor. However, as we plot x1 along the horizontal axis and w1 along the vertical axis, we plot the inverse demand functions. And as a result, our x1L will be flatter than that of x1S. So this will be the presentation. This will be the long run factor demand and this will be the short run factor demand. This will be flatter than this. Is it understandable? The mathematical part, how we will have the consistency exercise as we consider the inverse demand function. So please check everything and tell me whether you are understanding the matter or I need to repeat any part. So this is fine to all of you, I hope.
Ma'am, can you please repeat that part once again?
Which part, Udita?
Ma'am, that both are negative, so that absolute value part.
Okay. So are you, are you confident with the fact that both the derivatives are negative?
Yes, ma'am.
Okay. So if both the factors are negative, suppose it is 10. So minus 10 and this is also negative. So suppose it is 8. Okay. It is minus 8. So it is minus 10, minus 8. So minus 10 plus 8. এরকম হয়ে যাচ্ছে তো?
Yes, ma'am. Acha, I understood.
আর যদি তোমার del x1s by del w1 greater than that of del x1l by del w1 হয়ে যেত, উল্টোটা যদি হতো, তাহলে কি হতো? minus 8 plus 10, তাহলে plus 2 হয়ে যেত।
Yes, ma'am. Yes, ma'am. Then it won't be negative anymore.
Okay. So you got the point?
Yes, ma'am. Thank you.
Mathematically, we need that the long run factor demand should be steeper than that of the short run factor demand. However, we will plot the inverse factor demand curves. So we will have flatter long run factor demand and steeper short run factor demand curves. The diagram will be like this. Okay. However, if I consider W1 along the vertical axis, X1 along the horizontal, W1 along the horizontal axis, X1 along the vertical axis, in that case, blue one should be the long run curve and the red one should be the short run curve. The same thing actually. Since we are considering the inverse functions, we are doing the reverse. That's all. Okay, so this is all about unconstrained optimization technique. Just I'll tell you to note one factor. So graphically, when we are plotting long run curve, short run curve, etc., here there is no question of enveloping the curve because the two lines are cutting each other. However, some idea is there, the long run curve will be flatter than that of the short run curve. Okay. Okay, so if it is a smooth curve like the long run average cost, long run, short run average cost, at this point there will be a tangency and then the curve will turn up. If it is U-shaped curve, up to this it will come like this and then it will move like this if it is U-shaped curve. So, and this can be considered as the long run curve. Okay, so from here the idea of envelope curve will come, and in context of constant optimization we will talk about how long run curve envelops the short run curves. Okay, so with this I'm completing the analysis of the unconstrained optimization, and now I'll shift for analysis of constrained optimization. Any question in between?
Ma'am, I did not get this. Means the tangency part where there are
That's
two
the storage you
intersecting.
don't need. Ayan, you a bit confused always, you need to check all the things repetitively, So if you don't understand, it's fine. In context of constant optimization, when the idea real long run cost, short run cost, all these things will appear, then I'll talk about the point of tangency, because here there is really no tangency. So you need to really imagine this, So you,
Ma'am, but
Can
there in the graph,
please,
omega 1 is fixed. Means the factor input cost is fixed, but here it is changing. So that is why I was asking how we are graphically thinking that this point will be the tangency of LSE and
in
SSE.
case of economics, when we are going for the applications, if you don't have that imagination, everything you try to understand using the hardcore mathematics, then you will never get that kind of imagination, how the curve is U-shaped, how you will get tangency, etc. So if you don't get it, forget about this. Don't get it, forget about this, because here the two curves are intersecting. Okay, there is no issue or point of tangency here. Only in context of cost curves, when the curves are U-shaped, then the idea of tangency, etc. will come. So forget about that. Okay, so if you look at this thing from the hardcore mathematical point of view, there is no point of tangency. Forget about this issue. Okay. When we will go for the envelope curve in context of constant optimization, look at that.
Ma'am, I had a question.
Yes.
Ma'am, mathematically I understood why it will be negative, but ma'am, in the given graph, x1 shows the quantity and w1 shows wage, right? So how is it when the quantity is increasing, then how is it that it is negatively slow? How is it that they have an inverse relation?
Who are you?
Yes, ma'am.
Who are you?
Ma'am, Ananda.
Repetitively, we read all these things starting from the basic analysis of the demand curve. So in context of Marshallian, Walrasian stability, we did the same thing. When we are doing the mathematical things, in that case, we are not considering the inverse demand functions. However, when we are plotting it following the Marshallian convention, we are plotting always the inverse demand function. So here we are doing the same thing. Mathematically, we are deriving the slopes directly from the functional form. However, when we do the graph, we are following the Marshallian convention, that is the independent variable we are marking as the dependent variable we are marking along the horizontal axis. In case of mathematics, we do not do this. We consider x1 is a function of w1, that is the independent variable that should be plotted along the horizontal axis. The other variable, that is the dependent variable, that is y, that should be plotted along the vertical axis. Here we are doing the, so we have to plot. Okay, So when I am telling, mathematically to hold this condition, the long run curve will be steeper than that of the short run. Now, if we want to do it in the graph, I have to consider 1 upon del x1 L by del W1 and 1 upon del x1 S by del W1. And as I consider these inverse values, the sign will be just the reverse. I told long run will be steeper than that of the short run. However, to maintain the same mathematical relationship, if you consider the in fact the inverse functions, in that case you have to consider 1 upon del x1 L by del W1 and 1 upon del x1 S by del W1. So you have to consider these two things. Okay, and if you consider,
Yes, ma'am.
you have to consider the reverse concept. Steeper and the flatter, this will be reverse, isn't it?
Yes, ma'am. Yes, ma'am. I got it.
Okay, so that we did. And forget about envelope curve. I'm telling this to all of you. When we will go for the real application in context of constant optimization, we will do that. Here, I wanted to tell you, look, when we graphically plot the matter, the long run curve is becoming the flatter curve, short run is the steeper curve, and coming at this juncture, if it is U-shaped curve, there is a possibility that this will appear as the point of tangency and the curve will bend like this. So forget about this. Okay, so next we are moving for constant optimization. Here we will consider more than one variables, just like unconstrained in variable case. Here too we will consider more than one component, more than one variable component. Now the first part almost you did in your first semester. What is the meaning of concavity, convexity, quasi-concavity, quasi-convexity, etc. Okay, so this part I'll send you and check the definitions. I think you will understand everything. If anyone have any question in that case, I'll clarify the matter in the next class. However, I'll go through the slides to show you, these are the things you need to check to develop the notion of constraint optimization. In case of constraint optimization, we need this kind of definitions. You did all these things in the last semester. However, just I am showing this part, you need to develop the applications, etc. in context of constraint optimization. So I think everybody is familiar with this definition of concave function. If a function is concave f of x bar, that should be greater than equal to lambda f of x prime plus 1 minus lambda f of x double prime, where x prime and x double prime are 2 points along the function. X bar is the middle value, or weighted value. When I'm taking the weighted average, lambda f of x prime plus 1 minus lambda f of x double prime, we will get combining x prime and x double prime, actually we will be able to generate x bar, this kind of concept. So I have x prime, I have x double prime, and both x prime and x double prime belong to this fx. So on the basis of this x prime and x double prime, I can develop this x bar. Okay, and this is the f corresponding to this particular x bar. Okay, and this is f bar basically. That is, if I consider the convex combination of these 2 points, actually I am here. If I consider the convex combination, I am here. Okay, so this is typical x bar. This is the f corresponding to x bar. However, if I take convex combination of these 2 points, in that case, we will get the function at this point. Okay, so f bar is lambda f of x prime plus 1 minus lambda f of x double prime. This is f bar. So f of x bar, that should be greater than f bar. This is the rule of concave function. F of x bar is greater than this. So this has been written here. So I think you are familiar with this definition.
Yes, ma'am.
Yes, ma'am.
So Ayon, now I want your suggestion. Are you familiar with these things?
Yes, ma'am.
Did this thing in this way?
Yes, ma'am.
Okay. So next, this kind of definition, you are familiar with this kind of definition too. At this moment, a function is to be concave if principal minors of Hessian determinant alters in sign starting with negative. So if 1 1 less than 0, if 2 2 less than 0, if n less than 0, and then if I consider 2 by 2, f1 1, f1 2, f2 1, f2 2, that is h2 det. The first row is basically, these values are h1 determinant, these are h2 second level of values, this is third level of value. In this way we can move towards n level of value. So if this alter in sign, we will get a concave function, and this function will give us maximization. The concave function will basically give the maximization. Therefore this is also the second order sufficient condition of maximization. Now coming to definition 3, I have considered the definition of a curve. The first two definitions covered the functions, concave functions, and next we are considering the definition of a curve. So a curve is strictly convex to the origin, corresponds to the fact that as we move rightward along the curve, increasing x1 and decreasing x2, the slope of the curve decreases in absolute value. So if we think about our indifference curve, if we think about isoquant, that is the strict convex curves, we have experienced that keeping, as we continuously increase the volume of x1 and reduce the volume of x2, the slope of the tangent, that will be flatter and flatter and flatter. As we move from left towards right, the slope of the tangent will become flatter and flatter. So this is the thing. Okay. So this can be presented in this way, dx2 dy by dx or dx2 by dx1. If you take derivative with respect to this, x1, then you will get this kind of expression, and that will be negative. The slope will become flatter and flatter. Here x2 is a function of x1 along the curve, that is x2 is equal to gx1 along the curve. Therefore, using the quotient rule or the chain rule and using x2 is equal to gx1, we can also develop this kind of expression. So are you familiar with these steps and then these rules? Last day we used this expression. I think you mentioned that you are familiar. Are you familiar with these things? Yes or no? You did it in the last semester. You may forget the entire thing. However, I think you covered. Yes or no?
Yes,
ma'am.
ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So just you need to revise. That's all. I'm considering these slides, or I kept these things in my slide because we don't need all the things you did in the last semester. However, we need several important expressions. Therefore, I kept the things here. So you need to revise. Am I right? You know the things you need to revise. Okay, so in this context, the idea of level curve is coming, and it is found that if a function is strictly concave or strictly quasi-concave, in that case, that can be expressed by a strictly convex curve. Okay, the level curve will be strictly convex. If a function is strictly concave or quasi-concave, in that case, this function can be presented by a strict convex curve. So any function which is strictly concave is also strictly quasi-concave, but the reverse is not true and is presented by strictly convex to the origin level curves. Okay, so are you familiar with the thing that strict concavity indicates strict quasi-concavity, however the reverse is not true? You know all these things?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes,
You have to
ma'am.
revise these things, okay? You have to revise these things because repetitively concave function, strictly quasi-concave function, all these things will come. Okay, so you know, you should be very clear about these things. Strict concave, is the meaning of strict concavity? What is the meaning of strict quasi-concavity? Why we are considering the fact that if a function is strict concave, then it will be also strictly quasi-concave. However, the reverse is not true. Then why we can present the strict concave as well as strictly quasi-concave curve using the convex, strictly convex curve. These functions can be presented by strictly convex curves, etc. Because here our emphasis will be mostly on applications, you know, utility function, production function, these are the similar kind of thing. So if you consider utility function or production function, these functions are quasi-concave. However, when we present these functions graphically, you have the experience the indifference curve will be strictly convex to the origin. Isoquant will be strictly convex to the origin. Okay, so the level curves associated with the strict concave or strict quasi-concave curve will be presented by strictly convex curves. Next, you have to check the definitions of the convex function too. The reverse thing will happen. So for the convex function, the reverse thing will happen. The f bar, that is the weighted matter, will be greater than that of f of x bar. Okay. And you also need to check the definition we did using the Hessian determinant or principal minors of Hessian determinant. Here, all the principal minors of Hessian determinant, that will be positive. So if you consider the first principal minor or second or move towards nth principal minor, all the values will be positive. Actually, this moves towards the notion of minimization. In case of minimization, actually, we get this condition because a strict convex function gives us the minimization. So minimization takes place when these conditions hold. Okay. There is also a third definition. A function is said to be strictly convex if this expression f1 1 f2 squared minus 2 f1 f2 f1 2 plus f2 2 f1 squared greater than 0. Actually, this is coming from these expressions, you know. Just I have mentioned this fact because in context of bordered Hessian determinant, along with the second derivatives, the first derivatives will also appear. You know, the f1, f2, this will appear in context of the bordered Hessian determinant, which we will use in case of constraint optimization. Therefore, I mentioned about this definition too. So function is strictly convex when this condition holds, you know. So here I am bringing the first order derivative along with the second order derivatives. Now, any function which is strictly convex is also strictly quasi-convex, and is presented by strictly concave to the origin level curves. Just the reverse. In case of strict concave and strict quasi-concave function, we present the function using a strictly convex origin level curves. Here, just the reverse. If the function is strictly convex or strictly quasi-convex, it will be presented by strictly concave to the origin level curves. So anything which you didn't do in your last semester, anything, any point? Deepika, anything? Is there any points which you didn't do?
No, ma'am, everything was done.
Everything is done. Okay, so quasi-concave and quasi-convex functions. This also I hope you did. You did all these things?
Yes, ma'am.
Quasi-concave and quasi-convex functions you did? Okay. Okay. So you have the idea, you know, here f of lambda x1 plus 1 minus lambda x2, that will be greater than equal to minimum of any of this, f of x1, f of x2. Okay, so if this is the context, it will be the quasi-convexity, quasi-concavity, etc. Okay, so here minimum, here maximum. Okay, so you are aware of these expressions. And if you are not aware of the expressions, you know, I think you are not aware of these definitions of quasi-concavity and quasi-convexity. Did you do this definition using the bordered Hessian determinant?
No, ma'am.
No, ma'am.
Okay. This is the new definition. Okay, this is the new definition I'm adding here because we need this definition, you know. For the quasi-concavity or quasi-convexity, we need to consider the bordered Hessian determinant. In the last chapter, we used the Hessian determinant. Here, we will introduce the bordered Hessian determinant. So let's first see what is the meaning of bordered Hessian determinant, and then we will come back to this condition. Now, in case of bordered Hessian determinant, I'm considering the same metrics which I used in context of Hessian determinant, f11, f12 up to f1n, f21, f22 up to f2n, fn1, n2 up to fnn, etc. However, there is a border. There is a border attached, a row, an additional row, an additional column. And these borders are prepared using the first order derivatives only. So bordered Hessian is formed by taking the Hessian matrix and adding 0, f1, f2 to fn as the first column and the first row. That is the first derivatives of the function preceded by a 0. So this will be 0 and then the first derivatives. So this is the expression for the bordered Hessian determinant. Now, to define quasi-concavity and quasi-convexity, we use this bordered Hessian determinant. Suppose that f is a function defined on the real space and that f has continuous first and second order partial derivatives. This is must. Here, h bar, there is a bar, represents the bordered Hessian of f. If we find that bordered Hessian determinants, you know, or the principal minors of the bordered Hessian determinants alter in sign, you know, alter in sign, starting with positive. Principal minors of bordered Hessian determinants alter in sign starting with positive. then a function is called a quasi-concave function. The function is called a quasi-concave function, and this will be associated with a convex curve. The function is quasi-concave, that means the associated level curve is convex in nature. Now here, why we are starting with H2? Why not H1? Because we need a border. We need a border. The smallest size of this one is given by this sector, 0 F1, 0 F1, F11. This is the smallest segment. This is the smallest segment. Okay. So the first component is only 0. So we start with this kind of thing. Then we can consider 0, F1, F2, F1. That 2 by 2. 0, F1, instead of F1, F11, we can bring this part, F2, F12. Okay. In the similar fashion, we can move on like this. So it starts with the notation 2, because the minimum order of the determinant or minimum order of associated matrix will be 2. Otherwise, you will be not able to put any border. So here, if H2 bar is greater than 0, H3 bar is less than 0, that is alter in sign. In that case, it is quasi-concave. Alternatively, if all the values are less than 0, in that case, it will be quasi-convex. If all the values are negative, it will be quasi-convex. Okay. So there is some difference between the concavity and convexity definition we derived or we mentioned using the Hessian determinant. You know, in case of minimum, actually we got all the values are positive. In case of maximum, we considered the alternate in sign starting with negative. So there is some difference. So please write down all these things side by side and check what are the differences. In the first line, I forgot to mention, the last sign can be positive, can be negative, depending on whether n is even, whether n is odd, etc. Okay, and this note is important. And whatever proofs you did in the last semester, please add those proofs here, because all these things are very important. Quasi function is not the reverse is not true, not necessarily true. Okay, this is important. In these slides too, you will get the things, when F2, etc. are positive, you are getting quasi-concavity. When F2 is not positive, you are not getting quasi-concavity, etc. So all these things are also there in these slides. However, it will be best to check these slides and add several points which you learned in the last semester. Definition 2 is okay to all of you?
Yes, ma'am.
Yes, ma'am.
Very good. Okay, so here I have considered the dimensions, If I use the notation 1 for these, 1, remember, it is 2 by 2. Some books, Hoy present the things in this way because Hoy actually considers these as the order of the determinant. So they are starting with 2, and in Chiang or in some other books, they use also the notation 1. It doesn't matter whether you are writing 1 or 2, etc. So remember, when you are considering the first principal minor, you have to consider the first principal minor of the Hessian determinant along with the border. So if you can remember this thing, that's more than sufficient. And you can generate several H1 bar, because not only this, you can consider the other values too. So you can generate a number of 2 by 2, you can generate a number of 3 by 3, etc. Okay, so the things will go on like this. The same thing which you did in context of Hessian, only you are putting the border. Only the difference is you are putting the border. Okay.
Ma'am, can you show the previous slide once?
Yes. Is it okay?
Yes, ma'am. But ma'am, in like one thing I was wanted to understand, like the k plus 1th row and the column elements. Like, if
Which
for
one?
example, no, ma'am, in the first line it was written we refer to matrix composed of first k plus 1th row and column elements.
Mhm. Okay.
Ma'am,
The matrix composed of first k plus one row and column elements leading to possible minus as you know. So suppose you will like to have one by one, if one only. Okay, so in that case, you have to add one more row and column. It means this thing. You need to add the border.
okay, ma'am. Okay, ma'am. Yes, ma'am.
Okay, you need to add one border, row wise and column wise. That it indicates.
Okay, ma'am. Thank you, ma'am.
Okay. Now, if you consider the first value, it is 0 minus f1 square, 0 minus f1 square. If you consider the first value, this value. So note that the first value in the border Hessian determinant is minus f1 square. Now, f1 square is always positive because it is a square element and there is a negative sign. So it must be non-positive. Okay. So this element is non-positive. So please remember this thing. You can consider this point as a note. Actually, we have to do a lot of applications. When we will go for applications, all these things will appear. So we need to put several notes here, need to learn several issues, need to put several notes so that when we will apply these notions in context of utility function, production function, we will be able to do all these things. Now, there are several exercises. Please do these things, okay? Because, you need to solve several bordered Hessian things that you didn't do in your last semester. So here there is no economics, just simply to help you, how to solve the matrix, etc. You can do these things. So show that the function f of x1, x2, which is x1 into x2 square, is quasi-concave, okay? So, you consider the bordered Hessian determinant and check whether your requirement is satisfied or not. If the requirement is satisfied, it will be quasi-concave. So there are several examples. Please check all these things. Okay. So up to this, you will be able to do all these things. And here there is the graphical presentation of the constraint extremum. So in case of n unconstrained variable case, we just considered the level curve in this way. I didn't bring any constraint here. Along with the level curve, or these functions, or this graph, we have the constraint. Here there is a constraint, here there is a constraint, okay? So whenever we are talking about a maximum or minimum, the maximum is this point. However, in case of constraint extremum case or constraint optimization case, there is no guarantee that you will be able to reach here. Okay, so this is the idea. Here, given this constraint, given the constraint G, given this constraint, okay, you have to find the maximum. You will be able to reach up to this point only. Okay. Given this constraint, you will be able to reach only at this height. So your optimum functions will be, or optimum values for x1, x2 will be this x1 star, this amount of x1 star, and this amount of x2 star. it will not correspond to this amount. It will not correspond to this amount. It will be given by this amount of x1 and this amount of x2. In the similar way, here also there is a graph like this, so if there is this constraint, so from this graph only we can go to this particular graph. So here also, the same thing can be presented in this way. With respect to this constraint, you have to find the values of x1 and x2. Okay, so this is the 3D context, this is the two-dimensional. So figure A presents a function f of x1, x2, which we want to maximize subject to the constraint g. Figure B presents the level curve corresponding to this f. So the level curve marked f star is clearly the highest level curve of f that can be reached while remaining on the g curve. While given the fact that I have to maintain this constant, I can reach only up to this curve. I can reach only up to this curve, this level curve. Okay. So this is the diagrammatic presentation of constraint extremum. Okay. So given the function, we will be not able to find out the maximum or minimum. Rather, we have to use the constraint. Now, how we solve this constraint optimization, or how we derive these values? The next question is, graphically, we are understanding we will be not able to reach at the maximum or the minimum of the function. Rather, we have to optimize subject to the constraint. Now, mathematically, how we will do this? Now, this is the function, objective function. Z is equal to f of xy. This is the objective function. And this we need to optimize subject to the constraint, say g of xy is equal to c. With respect to the same variables, I am setting the constraint, however, there is a fixed value. I have to maximize or minimize x and y subject to the fact that g of xy is equal to c, where c is a constant. So there is an objective function. The objective function is similar to that of the function we used in case of unconstrained optimization. The new thing is presence of this constraint. Now this constraint may be equality constraint or can be inequality constraint. Gxy can be equal to c, or gxy can be greater than equal to c, less than equal to c, greater than c, less than c. So all possibilities are there. In this chapter, we will concentrate on equality constraint. Next section, next unit will be based on inequality constraint. Okay. In case of objective function, we are not considering any inequality. Objective function is always equal to this. I have some objective. This will be presented by the equality sign. However, the inequality sign can be at least this amount, at most this amount. All these things can be there. So it can be equal to, it can be greater than, less than, etc. Okay. So in this chapter, remember that we are not bringing the issue of inequality constraint. Now, Lagrange did a wonderful job. Okay, it's a revolutionary mathematical development. Given several functions, how the functions can be joined and functions can be presented by a new transformed objective function. The original objective function is z is equal to f of xy. Lagrange showed that if there are single constraints, several constraints, how we can accommodate those constraints in a single function along with the objective function and can write a new objective function. Okay. Now, to have a new objective function, we need to incorporate the notion of Lagrange multiplier. Notion of Lagrange multiplier. So algebraically, what Lagrange is doing, writing a new objective function z equal to f of xy was there plus lambda, then the constant minus the objective. Actually, this equation we are writing as c minus g of xy equal to 0. Is there anyone who is waiting? So, I have to rewrite this the constraint as c minus g of xy is equal to 0. C minus g of xy, that is the constant minus the variable part, equal to 0. Okay, so this is the expression. Now, if you present the constraint as g of xy minus c is equal to 0, here you have to use the minus sign. Okay, so please take a note. Please take a note. If we write the constraint, or if we treat the constraint as g of xy minus c is equal to 0, the Lagrangian expression will be given by z is equal to f of xy minus lambda. Z is equal to f of xy minus lambda g of xy minus c. G of xy minus c. You will get the same result. You can write it in this way or you can write it in that way. Okay, any question up to this? How we will write the Lagrangian expression?
Ma'am, can you explain the Lagrangian form once again?
Yes. There was an objective function, okay, and a constraint. Okay. We are discussing the simplest case. You can have more than one constraint. Subject to more than one constraint also you may need to optimize. However, we are considering the simplest case where there is a single constraint. So Lagrange is showing that how this constraint can be incorporated in the original objective function using a Lagrange multiplier. So he proved that algebraically, if we add the constraint with the objective function using a Lagrange multiplier, we will get all relevant results. So here what we are doing, I have the original objective function f of xy. I like to maximize, say, x and y values. Then I am incorporating these constraints using a Lagrange multiplier. This kind of multiplier, after the name of Lagrange, we call the Lagrange multiplier. So the objective function plus the Lagrange multiplier into the constraint. Now, if you write the constraint as the constant minus g of xy is equal to 0, in that case, the sign here, the sign will be positive. If you write the expression as g of xy minus c is equal to 0, in that case, this sign will be negative. Negative minus lambda g of xy minus c. Lambda is the Lagrange multiplier. Now the meaning interpretation of Lagrange multiplier will vary from case to case. In case of utility maximization, lambda will be the shadow price. Whereas in case of cost minimization, output maximization, the interpretation of the lambda will be something else. Okay. So in particular context, we will give the interpretation of lambda because it will vary from case to case. However, the lambda in general is known as Lagrange multiplier. So we are bringing a multiplicative factor lambda, which we are multiplying with the constraint and adding it with the original objective function. Okay.
Ma'am, is the lambda constant even though it differs from case to case?
You know, lambda value, actually we will be able to take derivative with respect to lambda. You know, Lagrange multiplier is, since its interpretation will vary from case to case. Okay, so Lagrange multiplier will be considered as a multiplier. The value may vary from case to case. It's a multiplier. However, it's not that there is some universal value for this lambda. Okay, as the things goes
Yes,
on,
ma'am.
you understand. I'll come to that. Now, once we get this thing, then just like any optimization, I have to take the first order conditions. Just like any other optimization, I have to consider the first order conditions. In this case, we have to find out the values of x and y, and therefore we will take derivative of z with respect to x and y. And one more thing we have to do, that is we have to take derivative with respect to the Lagrange multiplier too. So we have to take derivatives with respect to all the variables we have in the model, and then finally we have to take derivative of the objective function with respect to lambda as well. Now, when I am mentioning about the objective function, I am typically mentioning about this transformed or revised objective function. Okay. So I have to consider del z by del x. Del z by del x will be f of x, actually del f of xy by del x, that I am presenting by f of x. Now here you have lambda c minus lambda g of xy. So from this we will get one del g by del x multiplied with lambda. So we are getting minus lambda gx. By first order condition, we will set this equal to 0, del z by del y. Similarly, fy minus lambda gy is equal to 0. If I consider del z by del lambda, we are getting back the constraint. Del z by del lambda is giving us nothing but the constraint. Okay, nothing but the constant. This equation, c minus g of xy is equal to 0. This is giving us nothing but the constraint. The practice is combining these two derivatives, that is del z by del x and del z by del y, we will form a new equation. Combining this and this, we will form a new equation, and that new equation will be solved or simultaneously solved with this equation, that is the constraint. So combining this and this, we will frame a new equation, and that equation will be solved with these constraints. Okay, for example, in case of utility function, we will derive the income consumption curve. Combining this expression and this expression, we will derive the income consumption curve or angel curve, and that we will resolve with this, that we will solve with this. This is the idea. Okay. In case of production function, we will consider combining these two, we will get the ISO cost line. Then using the ISO cost line and the cost constraint, actually we are getting back the constraint, we will solve for the values of output, etc. So, in the context, you will learn how we are combining and getting some meaningful equation, etc. However, in general, when we are learning, we need two equations to solve for two factors, x and y. X and y are the unknown components, and we have to solve for x and y. And for that matter, we need only two equations. So practice is, we will combine these two equations to generate a new equation, and with that new equation, we will solve this one. Simultaneously, we will solve the new equation along with the constraint. Okay. So if you combine these two equations, fx is equal to lambda gx, fy is equal to lambda gy. So fx by fy will be equal to gx by gy. That will be the new equation. Fx by fy is equal to gx by gy. That will be new equation. That equation will be solved with this constraint. The value of Lagrange multiplier lambda at the optimal solution always tells us the effect on the optimized value of the function f of a small relaxation of the constraint. If we change the constraint a little bit, what will be impact on the optimized value of the function f? Okay, what will be the impact on the optimum value function of f if there is some small relaxation of the constraint? Okay, so this is the idea of Lagrange multiplier. This is the idea of Lagrange multiplier. Now it will, the particular meaning of, relaxing the constraint, the effect on the value function, this will vary from one application to other. So in typical context, again, we will elaborate the meaning of the Lagrange multiplier. To begin with, the common meaning or the standard meaning of Lagrange multiplier is, for a small relaxation in the constant, how the optimized value function f will change. Any question? I think it will be easier to understand if we look at one example. We want to find out an extremum. Okay, so z is equal to xy subject to this constraint, x plus y is equal to 6. Now we are combining this, xy plus lambda 6 minus x minus y. If you consider x plus y minus 6, don't forget to consider minus of lambda. Okay, so to have a stationary value, to have an optimized value, we are writing all these first order conditions. If you take derivative of this expression with respect to x, del z by del x, you are getting y minus lambda is equal to 0. And from del z by del y, you are getting x minus lambda is equal to 0. And from this, if I take derivative with respect to lambda, we are getting back the constant 6 minus x minus y is equal to 0. Okay, so x plus y is equal to 6 minus lambda plus y is equal to 0 minus lambda plus x is equal to 0. You may use Cramer's rule, you may not use Cramer's rule. Okay, this is not necessary that you have to use Cramer's rule. So from this equation, you are getting y is equal to lambda. From this equation, you are getting x is equal to lambda. So x is equal to y. So the equation you are getting, that is x is equal to y. From combining these two equations, you are getting x is equal to y. Okay. So if you replace y by x here, 2x is equal to 6. So x star is equal to 3. Since x is equal to y, both x star and y star will give you the value 3. Now, lambda here, for this typical exercise, lambda is either x or y. So the value of lambda, that will be also equal to 3 for this particular combination of x and y. For this particular combination of x and y, the value of lambda will be given by 3. And finally, if you like to find out the value of z star, final or optimum value of the objective function, you have to consider x into y, that is 3 into 3, 9. So this is the procedure. This is the procedure. Okay, so these are several examples. So please check these things, do these things on your own. Okay. This is a constraint maximization problem once again. So you will be able to check the bordered Hessian determinants too. I think you practice up to this, you know. So next day, I'll talk about how we are deriving the second order derivatives, etc. It will be a bit difficult to do, maybe a bit difficult to some of the people to do these things on their own. So, you know, first you try to grasp, revise the things, different definitions, etc. Then try to understand what is the meaning of constraint optimization. Try to understand the meaning of bordered Hessian determinant, and then you solve only the first order conditions using the Lagrangian multiplier. Don't need to check the second order conditions. Second order condition we will check in the next class. I'll start from that point, how we will framing the second order conditions.
Ma'am, will you send the PDF?
Okay, so if it helps, I'll definitely send it.
Thank you.
And as I mentioned, you know, when you will revise the matter, please check what you did in the last semester, because here everything is not there. So maybe some confusion may take place because I have kept only the necessary things here. I didn't keep the entire matter. Okay, so you may